Okay, so we will start with a review of what we had a few lectures ago. First, let's recall the exterior angle theorem. We have a triangle. Yes. Aaron and Jessica, let's turn on the camera. What's happening? Okay, and I will check with Jessica. Okay, Jessica, okay. Okay, Aaron, what's this theorem is about? Exterior angle theorem. Do you remember this?
Yeah, it's about something about turning left, then left, then left 3 times, and then yeah, like getting to the degrees.
Okay, that is a different theorem about exterior angles. The summation of exterior angles is always 360 degree. But this exterior angle theorem is about if we label this A, B, C. Judge, okay. Okay, don't do it. Judge, okay. It means this exterior angle alpha, the measure will be the summation of angle A and angle B, the summation of the remaining two angles. Aaron, remember that this one? This is the exterior angle theorem.
Okay, now I remember.
Okay. So what you mentioned is another theorem about exterior angles. Okay, then let's recall this as the first theorem about congruence, SAS. Okay, George, what does this SAS stand for?
Side angle side.
Side angle side. Okay, so it means if you have a pair of triangles, that if a pair of sides, same length, another pair of sides, same length, and the angle between them, same measure, then they are congruent. It's very important to keep the order. Second theorem. Jessica, what's this SSS theorem stand for?
Side. Yeah.
Okay, all three sides. So it's side, side. If we have two triangles, first pair of sides, same length, second pair of sides, same length, third pair of sides, same length, side, then they are congruent. Aaron, ASA, what does it stand for?
Angle, side, angle.
Angle, side, angle. Okay, we have first pair of angles, second pair of angles, and the side connecting them. then the two triangles are congruent. Okay. So here it's very important to pay attention to the order. If the order changes, we may have different situation. Okay. Another very useful theorem that we learned last time. We consider a triangle. The longer side, larger angles. Longer side space of bigger angles, larger angles. More precisely, A, B, C. For this triangle, AB is shortest, less than AC, less than BC. From there, we have the corresponding theorem about property about angles. AB facing angle C, AC angle B, BC angle A. Okay, so longer side, larger angles, shorter side, smaller angles. It says these two are equivalent. Okay, let's take a minute to recall how did we prove this. Fred, can you hear us, Fred?
Okay.
Okay, let's turn on the camera. Okay. Aaron, do you remember the proof?
I'm getting into it. Hold up.
Okay, so we proved this in 2 steps. So a brief review. First proof. Longer side
Perfect.
implies larger angles.
Oh yeah, there's a point D on the BC line, right?
Yes, yes, yes. So how do
Therefore,
we
with the
prove this?
CD and AC.
Yes. So because this is longer, we can have a point. We already have, let me make it more precise over there. Pick a D with A, C, D, C. Then these two angles are the same. So angle B less than angle ADC, which equals angle DAC, because have the equal length. This is less than angle A. Okay. That's the first part of the proof. Second part of the proof. So larger angles imply longer side. But this one, we use the proof by contraposition. This theorem has a very important application. Longer sides, larger angles. Okay. Application is the following. Triangle inequality.
Wait, so when we want to prove this, we just basically draw lines.
Which one?
Like the triangle one.
Do you mean this theorem?
Yeah, we don't. Actually, no, never mind.
So we proved this last time. So this is a review of how we prove it.
Yeah, I thought it was like something different.
Okay. So what you said, maybe the next one, triangle inequality. For any triangle, A, B, C, we have that the summation of the two sides is always bigger than the third side. Even though the third side may be longer, but the sum of the two is always bigger. This is called triangle inequality. Okay, it's about the relationships between the three sides of the triangle. So to prove this is we will extend AC. How far do we go? We stop when we get to D with AD equals AB. Then we construct the triangle. BCD. This implies AB plus AC, AD plus AC, which, so AD plus AC is just the CD. Now we need to check in this triangle. This is the longer side than this one. You need to check this is the bigger angle than this one. So CD longer than BC is the same as angle CBD bigger than angle BDC. And we can check this easily using the property that these two sides have the same length. So this angle and this angle, they have the same measure. So the whole angle is bigger than a part of it, which is equal to this. So we can check this quickly. So this is true, then this is true. Triangle inequality. Then we introduce another geometric object, parallelogram. A parallelogram consists of two pairs of parallel sides. And label this A, B, C, D. So the definition A, B parallel to CD, A, D parallel to BC. Okay, so this is what we used in our definition, then we prove the following theorem. Part of this in the lecture and part of it in the homework. Equal length A, B. If they have the same length, then the two must be parallel. This is the equivalence. So a pair of conditions, second pair of conditions, they are equivalent. We used this part in our definition of a parallelogram. But because they are equivalent, you can also use this in the definition of the parallelogram. It doesn't matter which pair you choose, as long as you use the whole pair. Then a very important property about the parallelograms is their diagonals bisect each other. So we call this two the diagonals. If I connect, okay. Okay, so this means the two segments AO and OC same length, BO and OD same length, bisect each other. In our homework, we consider a special parallelogram where all four sides have the same length. Recall that when we had in our homework, if in particular, it satisfies this pair of identity. So this is a parallelogram. It's a special one. We call it rhombus. Okay, that's something we learned in the homework. Okay, today we will go a little bit further. We will introduce a very important theorem called the midpoint theorem. In different books, maybe different schools, they have different names for this theorem. Some may call it midsegment theorem. Some may call it midline theorem. They all mean the same thing. Okay, so what does it say? We start with a triangle. We consider a triangle. We pick the midpoint of BC. Then we draw two lines through this midpoint. One parallel to AB. Another one parallel to AC. So this point, AB, this will be F. Okay. Draw EF parallel to AB. And EG parallel to AC. So we have two more points, F on AC, G on AB. Then we connect these 2 points. Okay. So initially, we only know that E is the midpoint. This line is parallel. We don't know if F is the midpoint yet. We don't know if G is the midpoint. So the theorem tells us F is the midpoint. AC. G is the midpoint. Of AB. Okay, pay attention to these two properties. They are not given in the construction. What we know is these two lines are parallel. These two lines are parallel. And we want to prove that this is the midpoint. And this is another midpoint. Okay, that's something we needed to prove. Second, so we connect the 2 points, we get a third line, and we want to prove that this line is parallel to BC. And lastly, the 3 sides. Oh, maybe we can make it this simple. We just see GFG is half length of BC. EF half size of AB, and EG half size of AC. Okay, a little bit long and a very difficult theorem. Let's take a moment to analyze this. Okay, so in the proof, George, what are you doing?
Taking notes.
Oh, no, you are not taking notes. Okay, so, okay, perfect. Okay. What we know and what we want to prove, we will keep the two separated. Okay. Don't mix what we know with what we want. Okay, so in a proof, I will check with you what we know. What do we want? And the key is how to get what we want. Okay. What do we know over there? We know E is the midpoint. We know these two lines are parallel. These two lines are parallel. That's all. Now let's check why F is the midpoint of AC. How do we verify this? How do we verify these two sides have the same length? We cannot compare them directly, but we can compare it through a middleman. They both compare to EG. Let's check. Okay, we will start our proof. For the first one, to target what we wanted to prove. AF plus EG and CF equals EG. Okay, so if we can prove these two identities, then AF and CF, they both equal to EG, so they have the same length. In particular, from there we conclude. Okay, so let's get this out of our way. Implied, I miss an I over there. Okay, let me check. Jessica, what do you think about this statement? Does this follows from the identities. If we can prove AF and EG, AF and EG same length, CF and EG same length, then I claim these two must have the same length. Do you agree? Okay, because they equal to the same thing. Okay, how do we check this one? Why AF and EG must have the same length? Fred, what do you think? Why? George, what about you?
Because they're parallel.
All right, okay. Because by the construction, these two lines are parallel. These two lines are parallel. So this is a parallelogram.
A rhombus? You said there was a rhombus before.
Nothing, we don't know. So these two same lengths, these two same lengths, but these two may have a different length, right? So it's not necessarily rhombus, but just a parallelogram, and that's what we need.
Okay, I see.
Okay. Okay, so the key point, because the lines EF Fred, pay attention to the lecture, Fred. EF parallel to AB. EG parallel to AC. This implies AFEG. Being a parallelogram, the two parallel sides must have the same length.
Yeah.
Okay, this implies AF EG and AG equals EF. Okay, we obtained the first part. Now the second part, CF and EG. How do we prove they are the same? So previously, we used this parallelogram. Could we use this parallelogram? Aaron, what do you think? Is this a parallelogram?
Yes.
Why?
Well, let's see. GF and EC are parallel, and so are GE and FC.
GEFC parallel. Okay, that's the condition. What about this pair?
GFEC?
Uh-huh.
Yeah, they're
Are
also,
they parallel?
yeah.
Why? So did we see it in the theorem?
Hmm?
So this is what we want to prove.
Yeah.
We wanted to prove that we haven't. So what we want, this is what we want, not what we know. We don't know it yet,
Oh.
right? Okay, we wanted to use that, but we cannot because we don't know yet if they are parallel. If we know they are parallel, then we could, but now we don't.
I guess we can all use GE and FC then.
GE and FC. So this is not good enough. Okay, so what we do is we will use the following. Let's consider the following pair of triangles and check if they are parallel. 1.1, 1.2. Triangle BEG. Triangle ECF. Can we prove that they are congruent? What do we know about them? We know that E is the midpoint. In particular, these two sides have the same length. That's what we know. Anything else do we know from the construction? To prove they are congruent, we have three choices: A, SA, SAS, or SSS. Which one can we apply?
I think ASA.
ASA, so we have one S. What are the angles? I'm going to label this angle 1 and angle 2. Angle 1, 2. Okay, let's check. Angle 1, angle 2. Do they have the same measure? George,
I think.
what's the reason for
Well,
this?
because
Why?
look. It has like, I just don't know. It's common sense.
No, you cannot say common sense.
Oh, you show what it says it.
No, okay. So why these two angles
Well,
have the same measure?
technically, if you draw like a over G here, that means these two angles, like the inner angle of like the intersection of G and F, the thing is like the same. So if these two are the same, like, and then like the angle two is the same.
Okay, use what we know in the construction. Could we use this condition, George?
Oh, yes.
How?
Well, it's parallel, so that means like you kind of like said it last class. It was kind of like,
Okay, because these two angles are the corresponding angles for the two parallel lines. Therefore, they must be the same.
yes.
Okay, so
It's
note, I want you to remember the argument for this because the two lines are parallel and they are the corresponding angles. Angle 1, angle 2. Okay, next pair. 3 and 4. Why are
Hey,
they the same?
teacher, can I ask a quick question?
Yeah, sure.
Just like the same, can you like, if you're like trying to prove something like a rhombus or something, can you still draw a triangle?
Yes. For example, over there we have the rhombus. If we connect the vertices, you should get a triangle.
Yeah, makes sense, makes sense.
Okay. Let's get back to the proof. Okay, Aaron, angle 3, angle 4, I
They're also
claim
parallel
they have the same measure. Why?
because
Which condition we can use?
we can use F as a midpoint and they're parallel.
So we don't know this is the midpoint.
I mean, GE, they're basically lines GE and AC and they're parallel.
So GE and AC, they are parallel.
And they're
Therefore, the two angles, they're corresponding angles. They
yeah.
have the same measures. Okay. We also have 3, angle 4.
Wait,
Okay, Aaron.
we could also use let's see, hold on, wait. Well, since we know that angles 3 and 4 are parallel, then
No, the lines are parallel, angles same measure.
I mean they're corresponding.
Okay.
And then I see on the notes is we can use the EG equals CF, therefore we can assume since they're parallel.
E G
Or I mean
C
GE, fine, GE.
G E.
Wait, teacher,
Uh-huh.
does it really matter if it's EG or GE?
Most of the time it doesn't matter, but sometimes we want to see two triangles are congruent, so we have to make sure the orders are correct.
Okay, I'll just call it EG equals CF.
Why?
Because as you can see, angles 3 and 4 are corresponding.
Okay, so the two angles are the same. Why? The two sides have same length.
Well, we can. Oh, wait a second.
What theorem do you apply?
I forgot what it's called. Hold on. I'm gonna check my thingy and see what's called.
Okay, so here we have a side and two pair of angles. So this will be the ASA. Two triangles.
Oh
B.
yeah, right. ASA. I thought it was called the SS. I thought it was SSS, but then I remember it was ASA.
Angle ECF. Okay, now what we have done? We proved that these two triangles are congruent. In particular, the corresponding sides have the same length. Okay, so this is the second pair of identity we need for the first part. We proved this one here. We proved this one there. Combine the two, we conclude F is the midpoint. Okay, any question about this part? We finished a little bit, make some progress. We proved this one. Okay, let's take a 5 minute break and we will resume the proof after the break. And think about this and let me know if you have any questions. The 5 minutes
Okay.
break, be back at 18.
Okay.
Okay. One and two, the corresponding angles of these two lines, which are parallel, so the two angles are the same. 3 and 4, they are the corresponding angles of these two parallel lines. Therefore, they have the same measures. Then we have angle, side, angle theorem. The two triangles are congruent. In particular, these two sides, same length, two sides, same length, so F is the midpoint. Okay, so for this one, we proved that F is the midpoint. Let's put a check mark. Okay, what about the second one? G is the midpoint of AB, and how do we prove this? George, do you want to say something?
No, I thought I know something, but then I figured out no, I don't.
Okay. We prove that F is the midpoint. Now we want to check if G is the midpoint.
Can we just use the same way that we proved F?
Okay, that's a correct direction.
I mean,
We
that's
will,
basically how you do it.
yes. Okay, but we are almost there. Just a few more steps. The two triangles are congruent. For the previous step, we used this pair. For the next step, we use this pair of sides. They are congruent, BG and EF. Okay, now let's group these two together. What can we see about these two identities? The first one, C. Okay, I circled the wrong pair. Let's circle the other pair. A F C F. I circled this pair. I want to circle this pair with this pair. Okay, the first one tells us AG and EF same length. Second one, BG and EF same length. Aaron, what can we say about AG and BG?
They are the same length.
They're the same length because they equal to the same thing.
Well, yeah.
Okay, so here we have AG and BG, they both equal to EF. So G is the midpoint. Okay, so we proved this one. We put them one by one. Okay, now we want to check that FG is parallel to BC. Okay, let's see how we prove this. Why the two lines must be parallel? What theorem can we use? Okay, see, we start with the size. Let's compare this triangle AGF with GBE. First, we know AG and BG same length because G is the midpoint. We just prove it. And we know that GE and AF same length. What about the angles? Are these two angles the same? Jessica, what do you think? Angle A, angle BGE. Do they have the same measure?
Yeah.
Why?
Because
5.
all the like triangle like lengths are the same.
Okay, so a simpler reason is these two lines are parallel. I claim these two angles must be the same. Tell me why. Because EG is parallel to AC. Why? These two angles must be the same. as long as the two lines are parallel. Because they are the corresponding angles. So because EG is parallel to AC, angle 5, angle 6. Again, we know that AG and GB same size. AG, GB. We also know AF and GE. Now we have the side angle side theorem, the two triangles AFG, GEB. Okay, side angle side theorem. We'll go back to the graph. This pair of sides equal length. This pair of sides equal length. The angle between them equal measures. So side angle side theorem. The two triangles are congruent. They are congruent. The corresponding angles will have the same measure. So now I will label this angle 7. Aaron, these two triangles, what's the corresponding angle for angle 7 over there?
Angle 1.
Angle 1. So the two triangles are congruent. These two angles must be the same. Angle 1 and angle 7.
It can also be angle 2, but yeah.
Okay. Let's stick with angle 1 equals angle 7. Okay, now let's go back. The two angles same measure. What can we say about these two lines? Jessica. 1 and 7, same measure. What about the lines?
Wait, could you repeat that? I couldn't hear it.
Okay, so we know that we just proved these two angles have same measure.
Yeah.
From there, what can we say about these two lines, EF and BC?
They're parallel.
Why? Why is that? Yes, they are, but why?
Because those two angles are the same, and
Because these two angles are the corresponding angles of the two lines, equal corresponding angles. This implies the two lines must be parallel.
Mhm.
Okay, very nice. So this implies FG parallel to BC. Okay, we finished this part. Okay, let's see what's remaining. FG is half of BC. Is this clear, easy or not? Think about this one, easy or not? George, what do you think?
Well, before you explained it, it was hard. After you explained it, it was easy.
Okay, so why? Okay, how do we prove that this is half of FG is half of BC? How do we prove this? Think about what we know and what we want. Let's see, how did we prove? Okay, let's start with the easier one. Maybe, let's see, this one. EF is half of A, wait a second. EF is half of AB, and EG is half of AC. Okay, maybe start with this one. why EG is half of AC? Aaron, have any thoughts on this?
Oh yeah, angle 7's course. I mean, yeah, angle 7's sort of corresponding with.
No. The different question. EG is half of AC. So how do we check this?
Oh, we know about AG and EF, I think.
So EG and AC.
Mm-hmm.
What we know is AF, GE same length.
Yeah.
CE, GE same length. Is this enough?
I think so.
Okay, because
Oh, wait a second.
this have same length, this have same length, so they together with twice of the length. So because, for example, the third, okay, so this is the second part. Third part, we know that AF equals EG equals CF. This implies EG is 1/2 AF CF, which is AC. Okay, now the second part. So we check this one. Let's move to EG. We check this one. Okay, maybe the wrong one. What about this one? EF is half of AB. Why is this? Aaron, yes.
We know that EF, hold up, right, we know that AG equals EF, and that,
Wait a second. We know EG equals EF? No, we don't.
no, AG equals EF.
AG, yes, okay, nice, okay.
And then since BG equals AG, then we know that, yeah.
Okay, so the both equals to EF, so EF will be half of the sum. Okay. So AG EF equals BG. This implies we proved another one. Okay, one more left. FG half of BC. We will do the same thing because the two triangles are congruent. So GF and BE same length. And E is the midpoint, these two same length. So all three same length, they'll be half of the sum. And this time, B. we proved last part of the theorem. Okay, so let's have a brief review of what we have proved. This is so-called midpoint theorem. If we focus on the 3 points, the midpoint. If we focus on the 3 segment, then this is also called midsegment theorem. If we focus on also some midlines, the lines go through the midpoints. So 3 different names for the same theorem with different emphasis. The first one emphasizes on the points. All 3 points are the midpoints. Second one focus on the segment. They're all mid-segments. The last one focus on the lines through the midpoints. Okay, so
Those 3 tiles are basically, you're saying the same thing, basically.
they are saying the same thing, but from different perspective.
Oh, I see.
Like we have a cube in a space. Someone sees it from the east, someone from south, someone from north, someone from up, someone from down. Different perspective, but the same theorem. Okay. What we know, so our assumption, we start with 1 midpoint, 2 parallel lines. Okay, so that's where we start. 1 midpoint, 2 parallel lines. And then we proved both are midpoints. That's what we proved, not by construction. And this is parallel to the third line. And each of this is half of the size of the corresponding edges. Okay, a very important theorem. And then we will use this in our next chapter about the similar triangles. So you can see the proof is kind of long, and each one takes a while to complete the proof. We have to use the properties of parallelogram, properties of congruent triangles, parallel line. We used everything we know to prove this. Okay, after the class, I would suggest you review the proof and go through it again to see the steps and how we connect all the steps. Okay, so this is the midpoint theorem. And this triangle that connect the 3 midpoints, we call them middle triangle. Okay, so by our midpoint theorem, by this theorem, the triangle obtained by connecting the midpoint with the 3 segments will be parallel to the corresponding sides. And they will be of the half size. So from this theorem, we have a lot of consequences. Next, we want to generalize this. If I start with the triangle, if I go to the midpoint, we know they are congruent, they are parallel. A, B, C. What if we go to the quarter point instead of midpoint? If I call this I and J, is I, J parallel to BC? Think about how to prove it. George, what do you, an idea? How do you prove this
No.
quarter point?
Like I and J or just like which quarter point?
Okay, so these are the midpoints. These two are the quarter point.
Quarter
one,
points? I don't know for quarter points, sorry.
So it will be the mid of the mid. So 1/2 of 1/2. So it's 1/4, right? Okay. So I and J, mid of mid. 1/2 of 1/2, 1/4. Aaron, what do you think? Are they parallel? How to check?
I said the way to check is like to do angles like SAS or ASA, I think.
Okay. Could we use the mid segment? Could we use this too?
I don't see the oh. That's not a triangle.
Okay, so let's apply our midpoint theorem. The midpoint, these two lines are parallel. Do you agree? Jessica, what do you think? The midpoint, the two lines must be parallel. That's what we just proved. Okay, that's the first part by the midpoint theorem. We have EF parallel BC. Now we consider the smaller triangles. Let's apply the midpoint theorem to this one. We apply the midpoint theorem to ABC. Then we apply the midpoint theorem to AEF. What can we conclude from there?
We could do a point somewhere between E and F, I guess.
So what we know is I is the midpoint of AE.
Yeah.
J the midpoint of AF.
And I'm saying we should do a midpoint in the middle of EF.
Okay, we could do that, but here we already have two midpoints. So we will
Okay.
use what we have.
All right.
Okay, we already have this, so we're going to use it. I claim these two lines are parallel. Why?
Corresponding angles.
Okay, we have the most recent theorem, the midpoint theorem. Because I and J are the midpoints of the segments. So we apply the midpoint theorem to the smaller triangle with their midpoints. Now if we combine the two, we see that IJ must be parallel to BC. Okay, let's consider another situation. Let's consider is so this is 1/2, this is 1/4. Okay, instead of the midpoint, quarter point, we have 1/3 point, 2/3 points on a segment. 1/3 point, 2/3 points on the segment. Let's label them E, F, I, J. Again, we want to check whether the lines are parallel. If we want to apply the midpoint theorem, we can apply to this one. A, E, F. Total 2/3, and this is 1/3. 1/3 is half of 2/3. So for this triangle, A, E, F, this IJ is a midsegment. Right? Then we can apply our midsegment theorem. Let's also find the 1/3 point. Maybe try to keep it precise. This will let's label this IJK. Okay. If we look at this triangle, midpoint, midpoint, we have the midpoint theorem. We have a lot of parallel lines. So eventually, we want to generalize this. So the midpoint theorem, let's recall what the midpoint theorem tells us. If it's 1/2, then the lines are parallel. A, B, C, F, G. So if AG over AB is 1/2, AF over AC is 1/2, by the midpoint theorem, GF is FG parallel to BC. And the theorem we had over here, if we apply the mid theorem twice, not only half, but 1/4 had the same property. So this will be I and J. AJ over AB is 1/4. AI. JAC. Applied mid theorem twice, we see that IJ also parallel to BC. So the generalization is no matter what this number is, as long as the ratios are the same, then the lines will be parallel. So generalization. A general triangle, a general line, A, B, C, E, F. If AE over AB equals AF over AC, then EF is parallel to BC. So it's a generalization of what we had from the midpoint theorem. The midpoint theorem tells us if this all equals 1/2, we have the parallel lines. If we apply it again, 1/4, we also have this. Then 1/3, 2/3 for any number, as long as the two ratios are the same. The two lines will be parallel. Okay, we will learn more about this next time. We will stop recording here and I will check if you have any questions.